Vanakkam, welcome to this video on biomechanics. In the last few videos we have looked at time dependent deviations from elastic behavior, that is viscoelasticity in biological materials. Specifically, we looked at three models of viscoelasticity, which is the Maxwell model, the White model and the standard linear model or the Kelvin model. In this video, we will be looking at viscoelasticity in one particular biological material, that is bone, or we will be looking at the viscoelastic modeling of bones. So, the stress developed in a bone is not just dependent on the value of the applied strain, but rather also dependent on how fast or slow the strain is applied. So, it is not just the absolute value of the strain that matters. Of course, the absolute value of the strain matters, but that is not the only factor. How fast or slow you apply that strain also matters. So, for a given strain, the applied stress is larger when that given strain is applied very fast. But then what do you mean when you say fast and slow? What is fast application of strain and what is slow application of strain? That is not clear. We need to discuss that. We will discuss that. But if you apply strain fast, then the stress is larger. So that means what? That means that the stress and strain are not purely linearly related. It is not like if I apply a larger strain, the stress will be larger. Yes, that will happen even in an elastic material, but not just that, right? If I apply a given strain faster, I will develop a larger stress. Means it is not merely the strain that matters, but also the strain rate that matters, or the time rate of change of strain matters. Okay, the time rate of change of deformation or dx by dt matters. So that means that there are other things that come into the picture, and these are manifestations of viscoelasticity, which we can try and model using our previous understanding of viscoelasticity. For example, we can start with the Kelvin model and try to predict what would happen in bone. Okay, let us make that attempt. Also, the strain response depends on how fast or slow the stress is applied. So, when you apply a stress, what happens to the strain response? So, suppose for a given load, you apply that load very fast, then the deformation is low. The same load, if it is applied over a period of time, then the deformation is high, right. So, that means the rate of loading, the rate of force loading matters, that is df by dt also matters. Let us say that we are applying a load f naught that varies linearly in time between time 0 and time t equal to capital T. This is t equal to 0 and this is t equal to capital T, and there is a linear variation in force. I am measuring experimentally what is happening in the bone. Okay, what is the experimental response of the bone in deformation, and I am finding something like this. This does not look linear, is it not? And it is not linear. Now, let us try to understand why. This is the experimental observation, or can we try and explain this experimental observation using our model, or is our model good enough to explain the actual experimental observation? Because if not, if our model is not able to explain the experimental observation, maybe either the experiment has not been conducted properly, which it is not. In this case, the experiment has been conducted properly, or the model needs to be updated. So, we can check whether the predictions match the experimental observations. This is bread, butter and water for all experimentalists. This is something that we do all the time. This is something that we do every day. We have a theory, we make a prediction, and then we do an experiment and check if that prediction matches with our theory. If not, either the experiment has not been properly conducted or the theory has to be updated. Daily life for a experimental researcher. Okay, let us proceed. So, the change, a linear change in force does not lead to a linear change in deformation is what we observe. Let us see what this means. In particular, our interest is to obtain a relationship between f and x that also incorporates capital T. The question is, does x of capital T depend on capital T, not small t? Of course, it depends on small t, but does it depend on capital T? Because if it does, that means the lower the window, let us go back to that slide and check. The lower this time window, the response will be different. The higher the time window, the response will be different. Is capital T part of your response equation? That is the question. Okay. Of course, small t will always be part of the solution. The question is capital T part of the solution? That is the question. Okay. Let us say the force is F naught by, let us say the force is F naught times T by capital T. That means dF by dt is F naught by T. What is our Kelvin model? What is our standard linear model? That is F plus tau epsilon dF by dt is equal to K2 times x plus tau sigma dx by dt. Now, this is the Kelvin model or the standard linear model. Now, substitute for f and dF by dt in this Kelvin model, that is F naught times small t divided by capital T. So, we rewrite this as K2 times x plus tau sigma dx by dt is equal to F plus tau epsilon dF by dt. What is F? F is F naught times small t divided by capital T plus tau epsilon times, what is dF by dt? That is F naught divided by capital T. Okay. Or let me rewrite this, that is K2 times x plus tau sigma times dx by dt is equal to F naught times small t divided by capital T plus tau epsilon times F naught divided by capital T. Okay. Or I can divide by K2 throughout. What will I get? I will get x plus tau sigma dx by dt is F naught by K2 capital T times small t plus tau epsilon F naught divided by K2 times capital T. What is the initial condition? Initial condition is x at time t equal to 0 is 0, or the deformation at time t equal to 0 is 0. Okay. Let us write this in the next slide, that is x plus tau sigma dx by dt is F naught by K2 capital T times small t plus tau epsilon F naught divided by K2 capital T with x at time t equal to 0 is 0. What is the form of this equation? This equation is of the form, what is the form? X plus a constant times dx by dt is a constant times t plus some other constant c, bt x plus a times dx by dt is equal to bt plus some constant c. Note that this is not the damping constant C. Okay, this is a different constant. This is not the damping constant. This is not the damping constant of the dash part. This is different. Okay. What is the solution to this differential equation with x at time t equal to 0 is 0? This has the solution x of t is bt plus c minus ab times 1 minus e power minus t by a. This is the solution. How do I know this? From my knowledge of differential equations. You know this from your knowledge of differential equations. Now check this form of the equation by substituting into the original equation, and you can actually try and find the values of the constants a, b and c. Okay. You can check that. I leave that as an exercise. Do that and also check whether this values of a, b and c are something that you can obtain from this. Okay. So what would be the final solution? The final solution would be x of t is okay. So this would be the final solution. This would be the final solution for deformation. So this is valid only when t is between 0 and capital T. This is valid only between 0 and capital T. Whenever time is between 0 and capital T, this solution is valid. Now when small t is much less than the time constant tau sigma, what happens? For small t that is much less than tau sigma, right, what would be x of t? X of t would be f naught by k2 minus c f naught, right, k2 squared capital T times 1 minus e power minus capital T by tau sigma. So when small t is much less than tau sigma, this would be the expression for deformation that I would get. This is approximately, this x of t is approximately, not exactly, this x of t is approximately f naught times small t by capital T times k1 plus k2. Now the question is, what would be the deformation at the end of the force ramp? That is, what would be the deformation at x of small t equal to capital T? When small t equal to capital T, the deformation x of capital T is, or rather let us rewrite this, the deformation x of small t equal to capital T is equal to f naught by k2 times minus c f naught by k2 squared capital T times 1 minus e power minus capital T by tau sigma. So this is the expression for the deformation when small t is equal to capital T. This is what I would get as the deformation. So at the end of the force ramp, this will be the deformation that I will get. This is plotted in this solution, right. In this figure, the solution is plotted, this solution is plotted. So that means, so what does this mean? This means when you say that you are applying the force fast or slow, what it means is that compared to the corresponding time constant, how fast or slow is the force applied, okay. Compared to tau sigma, in this case tau sigma is the time constant, compared to tau sigma, how much fast or slow is your time of application of the force. If it is comparable or if it is much smaller, the response is different, okay. So in these limits, x of capital T is f naught divided by k1 plus k2 when capital T is much smaller than tau sigma, and x of t is, and x of capital T is f naught divided by k2 when capital T is much greater than tau sigma. And this model does agree with the experimental observations. Right. What is the experimental observation? That deformation is lesser with faster loading and deformation is more with slower loading. This is what we observe in experiments and this is what we get with this model. So our model is able to capture with relatively good accuracy the experimental observation. That means that this is a reasonable model, okay. Of course, so that means again one more time, what is fast and slow? Fast and slow really mean how much comparable are your application times with respect to the corresponding time constant. That is what is meant by fast and slow. It is not a subjective measure, I think this is fast, I think this is slow, it is not our opinion. It is compared with that material's tau, is it not, tau sigma, that particular specimen's tau, okay. Compared with that time constant, how fast or slow is this, that is the question, okay. Of course, we have not really done the stress relaxation experiment. I request you to try that, okay. I will leave that as an exercise, I request you to try that as an exercise, okay. So with this we come to the end of this video. Thank you very much for your attention.